So chapter 9, we're going to continue on in chemistry. We're going to talk about chemical reactions. So for our chapter outline, we're going to have atoms, molecules. We're going to practice classifying matter. Then we'll talk about physical chemical changes, then chemical reactions, octet rule, chemical bonding, ionic bonds, and covalent bonds, metallic bonds, multiple bonds, chemical equations, balancing chemical equations, and then we'll talk about specific types of chemical reactions. So if you think back to the previous lesson, we defined an atom as the smallest elemental unit. An atom is made up of protons, neutrons, and electrons, and each atom is unique from the other, meaning hydrogen and carbon are both atoms, but they're different because they're made up of a different number of protons, neutrons, and electrons. Now, when we start taking the atoms and putting them together, we create what's called a molecule. So single atoms, two or more, binding together forms a molecule. Now, a single molecule is going to be the smallest particle that retains this characteristic chemical properties of the substance. So some examples are oxygen and hydrogen gas. Oxygen and hydrogen do not like to exist by themselves, so they form what's called a diatomic gas. And di always means two. Atomic means atom. So there's two atoms in these molecules. Ozone, on the other hand, is triatomic. So as you can imagine, this is three atoms of oxygen. Now, noble gases, remember that group 8A, very last column, are inert gases or noble gases. They don't like to make other compounds with anybody else. They already have 8 valence electrons. There's no incentive for them to do any sort of bonding or trading. So they are going to exist by themselves as single atoms, and we're going to call them monatomic, where mon or mono usually means one. So one atom. Now, in Earth's crust, 99% of all of Earth's crust, which is the thin shell we're going to talk about when we get to Earth science, is made up of only these 8 elements. The other 1% contains the other 83 elements, I think. So the majority of it's going to be made up of oxygen and silicon. Okay, and this is going to be important when we start talking about geology, because we're going to see that silicates are really the building block for all of our minerals, which then are the building block for all of our rocks. So they make up almost 75% of our crust. Then we have aluminum, iron, something we're familiar with here in East Texas, calcium, sodium, potassium, and magnesium. Okay, so you'll see these are group 1A and 2A. And then we have 2 different other metals. Okay? So now we're going to talk about classifying matter. Chemistry centers around studying matter. What matter is made up of, how matter behaves, how matter reacts, how we can convert matter from one to another. But even though we are focused on matter, we have to classify the matter in really specific ways because not all matter is the same. So our first type of classifying is going to be whether something is pure or it's a mixture. So a pure substance would be something that is homogeneous all throughout, meaning if it's made up of hydrogen, it's only hydrogen, nothing else. If it's water, it's only water, nothing else. A mixture is like anything, like a trail mix, right? Nobody would buy a trail mix thinking it's going to contain only raisins. No, a trail mix is going to have peanuts and raisins and M&Ms and all kinds of other things because it's a mixture. So within that branch of pure substances, we're going to have either compounds, which are really like molecules made up of more than one type of atom. And then we're going to have elements, which are made up of only one type of atom. Now with mixtures, we're going to have 2 different types. We're going to have our homogeneous, which are going to be uniform throughout, and our heterogeneous, which are going to be ununiform throughout. So pure substances is going to be something that is the same throughout and has a fixed, definite composition, meaning no matter where I scoop out of my container of water, it's always going to have water. Now a compound can be decomposed by a chemical change into simpler substances, meaning it can be broken down into its elemental state. So if I take sodium chloride, I can break sodium chloride into sodium and chlorine. If I have sugar, sugar is and it can be broken down into carbon and water. Whenever you burn sugar, that's essentially what you're doing, is you're boiling off the water and you're leaving behind a carbon substance, which doesn't smell or taste all that great. When we have an element, so the other type of pure substance, this is something that cannot be broken down into anything simpler by a chemical or physical change. So we can't boil it, we can't melt it, we can't freeze it. So it's going to only retain itself as an element. So, for example, hydrogen and oxygen. I can't break these apart into H and O. Okay, it's going to stay as H2. It's not going to break apart into H and H. Okay, not possible. So when we talk about 8 elements that make up the 90% of Earth's surface, oxygen, silicon, aluminum, iron, these are all examples of elements. Now, a mixture, on the other hand, is going to be where the composition varies from sample to sample, meaning each time I scoop out of the trail mix, I'm going to have a different amount of peanuts to M&Ms to raisins. They're not always going to be 3 peanuts, 2 M&Ms, and 1 raisin. It's going to be different each time because it's a mixture. And then the other thing is that mixtures can be separated by physical means, meaning if you don't like raisins, you can pick them out and you can only eat the parts you like. And so that's what also classifies it as a mixture. So a homogeneous mixture is where the composition is going to be uniform throughout the sample. It's not going to vary in one area from the other. So example, saltwater solution. If you've ever had to gargle salt water and you put salt in warm water and you stir it up, if you do that well and you don't put too much salt in, you should never at any point have more salt in one gargle than the other, because the sample is uniform because you mixed it really well. Now, the other type of mixture is heterogeneous mixture, and this is where you're going to have within a sample regions that have different properties. So some examples are coal and wood. I would say also you could think of trail mix, a salad. If you don't like, I love Olive Garden salads, but I do not like black olives, so I pick those black olives out each and every time. And so if you got a sample of if you got a scoop of the salad, somebody might get no olives and somebody else might get 10 olives. It's not uniformly mixed, but it's no problem because I can separate it by a physical means. As far as how to separate a homogeneous mixture, well, if you've ever thought about salt water and you were stranded at the beach and you needed to have fresh water, well, they make devices for that to separate the salt and the water so that you can then drink it safely without the salt in it, which would then further dehydrate you and make you more thirsty. Okay, so even salt water can be separated into salt and water by a physical means, which would be boiling. And then just so you know, it says, let's practice. There is a chapter 9 practice worksheet with 4 problems. So we have 4 separate practices we're going to do. So you can stop now and you can practice, or you can wait until the very end and practice them all at the same time. Physical and chemical changes. So physical change, if you think about what this means, it's going to result in a change in the state of matter. So solid to liquid to gas. But what we're not changing is the identity of the matter. So we're not changing who, we're just changing what who looks like. So instead of the water being an ice cube, maybe the water is liquid. Maybe the water is boiling. Okay, so that's changing the physical state without changing the chemical state, the chemical composition. So boiling, melting, condensing, freezing, evaporation, those are all examples. If it's a physical change, then it's going to only change the state of matter without changing the identity of the matter. A chemical change, on the other hand, is the exact opposite. This is going to alter the identity of the matter, producing a new substance with different properties. Okay, so most commonly the examples we think about are like cooking, so burning, cooking, spoiling food. Those are all examples of chemical changes. The other thing about chemical changes is that they tend to be what we would call irreversible. So if I'm cooking something, I can't uncook it. And once it's cooked, it's cooked. You can't unboil an egg. You can't unspoil food. You can't unburn wood. But I can take water that I've frozen to the solid state, and I can melt it back to the liquid state. And I haven't changed anything about the identity of the water, just the identity of the way it looks. Chemical changes tend to be irreversible. So sometimes this helps us in distinguishing between physical and chemical changes because one can be reversed and the other one cannot be. All right, chemical reactions. So chemical reaction is a change in matter in which different chemical substances are created by the formation or breaking of chemical bonds. So we're going to break bonds to form bonds, essentially. Now, all chemical reactions have a certain type of energy, which is a chemical energy, and this is potential, meaning it's the potential to do work. So if we were thinking about digestion, when you eat food and it breaks down the glucose and all the other nutrients you've eaten, those bonds that are breaking have potential energy for your body. And breaking those bonds down produces energy, which then goes on to run metabolism, make you feel good. You know, if you haven't eaten for a long time because you've been sick, you're going to feel poor because your body is being denied the chemical energy that it gets from food. Now, we use what we call a chemical equation to summarize in a symbolic way what is going on in a chemical reaction. So, for example, this is water plus carbon dioxide plus solar energy feeds the green plant and oxygen. And so this is known as photosynthesis. This is what plants do for us. Another type of reaction is plant materials reacting with oxygen to form water, energy, and carbon dioxide. And this is combustion or burning. So chemical equations, yes, they can be used with symbols here, but most likely the symbols we see are the ones that are formulas, which we're going to talk about in this chapter. Now, in a chemical reaction with the bonds breaking and forming, there's another thing going on, which is that the electrons are participating. Remember, protons and neutrons are housed inside the nucleus. They are not going to be exchanged, but the electrons are housed in the outer shells outside the nucleus and therefore are free to be exchanged. So those electrons that are in the outermost shell, we call the valence shell. They are the outermost electrons, and what they do is they determine the chemical properties of an atom. So when we think about our periodic table, we have rows. And mine's not going to have the right number of rows. But each row, we called that a column. We called each column a family or a group. And one of the things that they have in common are a lot of other properties, but they also have the number of valence electrons in common, meaning everybody in group 1A has 1 valence. Everybody in 2A, 2 valence. 3A, 3 valence. 4A, 4 valence. All the way to 8A, which has 8 valence electrons. The block that we don't really get to count is the B block, right here. The B group, they do not have a periodic or predictable number of valence electrons. So we tend not to study them so much in this chapter because they are transition metals and they can hold various numbers of electrons. But the ones that are in the A group, the 1A, 2A, all the way to 8A, the number in front of the A represents how many valence electrons that element has in that column. Now, what happens with these valence electrons is according to the octet rule. And this is that atoms are going to attempt to acquire an outer shell of 8 valence electrons. So what they can do is only one of two things. They can gain and lose them or share them. So if they gain or lose an electron, they can have 8. But if they share an electron, 2 elements can then have 8. And what we'll talk about, whether it's gained or lost or shared, is going to be based on whether the element is a metal or a non-metal and who it's trying to bond with. So for example, sodium. Sodium, when it's neutral, has 11 protons, 12 neutrons in the nucleus, 2 electrons in the first shell, 8 electrons in the second shell, and 1 in the third shell. So it has 1 valence electron because sodium is a group 1A metal. Now, if it loses this 1 electron, it will have 8 electrons in its outermost shell. Okay, so when that happens, it's going to then lose that third shell and have a full, stable second shell with 8. The only other option would be that sodium has to then gain 7 electrons in order for that to equal 8 in the third and be stable. And if you think about what's easier or harder, would it be easier for sodium to find 7 electrons from somebody else, or just to give up 1 electron and then have 8? And the obvious answer is it's easier for sodium to give up 1 electron and have 8 rather than try to find 7 other elements to get 7 other electrons from. Now, why are elements like neon in the 8A stable? Well, that's because their outer shell already has 8. That is their 8 valence electrons. Therefore, they're stable and they don't need to share. So we're going to take a break here and come back and talk about chemical bonds and finish up the chapter.